Hello everyone. In this video, I will be showing you a very fun little problem from I picked up from Lamau 2023. So Lamau is basically a contest which is organized by Indian uh, Olympic camp goers for the new coming batch to the International Math Olympiad camp. So this Olympiad is organized by the seniors for the juniors. Okay. So let's first read the problem. So determine the minimum positive integer k such that no matter how k positive integers, each at most 100 are chosen, one of them will divide the product of the rest. So basically what we need to do, we need to pick 100, we need to pick k integers and we need to keep on picking and we need to make a maximal set such that none of them divide the product of the rest. Okay, so one very cool way to do this is pick all the primes. So what you can do is you can go on picking 2, 3, 5, and so on till the last prime, which I believe is 97. So this set consists of 25 members, and very quickly you will realize that it is not possible to form a 26 members. For example, you cannot uh, insert any other member into this set because at least one prime will divide it. And if you try to remove one element from it, you will realize that you are able to add at most one element. So maybe most of you can figure out that 25 members is the highest answer. So 25 is the highest number such that none of the divide the product of the rest. So maybe our answer is k equal to 26. So this is our proposed answer. So let's try to see a formal proof of how we can establish this. So what we can do is first let me introduce to a notation to a notation. So Vp of n. So this basically means highest power of p dividing n. For example, let me give you an example. Suppose we take the number 60, and 60 can of course be written as say 2 to the cube, sorry, 2 square into 3 into 5. So this is the decomposition of 2. So V2 of 60, which means what is the highest power of 2 which divides 60. So we see that 2 to the power 2 is equal to 60. So V2 of 60 is 2, and similarly V3 of 60 will become 1. This is because 3 to the power 1 divides 60 and 3 to the power 2 doesn't divide 60. Okay, so this is Vp of n. This is the notation Vp of n. And now let's return to the problem. So suppose we pick a set with members say S1, S2 till Sn. And so suppose we know that, let's try to form the largest set such that S1 does not divide S2, S3 up to Sn. So when does this occur? So this basically occurs precisely when Vp of S1 is greater than Vp of S2, S3 till Sn for at least one prime. So let me elaborate this a little more. So what happens is, suppose say we take examples. Okay, suppose S1 equal to P1 to the alpha 1, P2 to the alpha 2, up to Pk to the alpha k. And suppose S2, S3 up till Sn will become equal to P1 to the power beta 1 till say Pn to the beta n. Okay, so suppose this is what happens. And suppose we assume that alpha 1 is less than beta 1 till alpha k is less than beta k. So this basically means that S1 divides S2, S3, S4, right? So this basically is the same as writing 2 square into 3 to the power 4, 5 square divides 2 cube into 3 power 5 into 5 to the power say 8. So this is basically what we are writing, and this is very easy to prove as most of you would be able to do. So thus we can conclude that Vp of S1 is greater than Vp of S2 till Sn for at least one prime, for one prime. Okay, and notice that Vp of S2 till Sn is equal to Vp of S2 plus Vp of S3 and so on till Vp of Sn. So we can basically conclude that Vp of S1 is greater than Vp of Si for all I greater than equal to 2. So we conclude that there exists a prime such that Vp of S1 is greater than Vp of Si for all I. So this basically means that suppose we write S1. So S1 has a prime assigned to it, say P, such that the power of P in S1 is the greatest among all the SIs, which means that suppose S1 can be written as P to the power K times beta, and suppose some random SI can be written as suppose P to the power L into beta 2, then we can always conclude that K is greater than L. Okay, so this is what we can conclude. So this is the basic condition we get, and this is true for all primes. So we know that S1 does not divide S2 till Sn, and similarly S2 doesn't divide S1 till Sn, where S2 is excluded, and so on. So Sn does not divide S1 till Sn minus 1, and each of them we can uniquely assign one prime. So suppose this is assigned P1, P2 till Pn. So we can uniquely assign each of these primes because P1 P1 has its highest power in S1, P2 has its highest power in S2, and Pn has its highest power in S. And these all are primes dividing S1, S2 till Sn. So P1 divides S1, P2 divides H2, and so on. So this basically implies that P1, P2 till Pn is less than 100. And of course, all of them have to be distinct. This means that n is less than equal to 25 because 25 is the maximum number of primes we can have from 0 to 100, from 1 to 100. And so this basically establishes that if S1, S2 till Sn is a set, then its maximum cardinality is 25. So this means that the highest set we can form satisfying this property is a set of size 25, and this basically means that if in the original problem condition if k equal to 26, we must have at least one of them dividing the product of the rest, one of them dividing the product of the rest, product of rest. So our answer is k equal to 26. So I hope you enjoyed this one problem. Thanks.